Hi folks! Today we're going to talk about section 4.2 from your textbook, Exponential Functions. Alright, so we're going to start off with this question. What is an exponential function? You've been spending a lot of time learning about something called power functions. Alright, power functions are when you have y equals a variable and you're going to have a constant in the exponent. And so an example of this might be that you have y equals x squared. That's a power function. Maybe you have y equals x cubed. That's a power function. Maybe you have y equals x to the 1/2. That's a power function. Any of these could be considered power functions because all of the constants are in the exponent spot. So what makes exponential functions different? An exponential function, right? We actually have the variable in the exponent spot. So that might be something more like this: y equals 2 to the x, or maybe y equals e to the x, or maybe y equals pi to the x. So anytime you have the variable in the exponent, that's considered an exponential function. And that's what we're going to be spending a lot of time talking about in this section as well as the next. Alright, so exponential functions. A general form for this equation is right here. F of x equals a to the x for every x in the real numbers, where a has to be greater than 0 and it cannot be equal to 1. Alright? So again, those examples we had before where we had y equals 2 to the x, or e to the x, or pi to the x, those all fit. Now there's going to be two main categories of exponential functions that we talk about. The first category is going to be the growth functions. And in a growth function, you're going to have a graph that looks like this right here below. Right? So it looks kind of like this. You'll know that it's a growth function if the a value in your equation is bigger than 1. On the flip side, you can have a decay function. And you're going to know that that's a decay function when the a value is between 0 and 1. And when that happens, the graph is going to look like this one. And we'll come back to the graphs in a little bit, but I just wanted to give us a little bit of a visual for what we are talking about. All right, so let's take a look at some exponential equations, solving them, and here we go. So e to the x, example 1. Example 1, 2 to the x minus 1 equals 2 to the 2x minus 4. One thing that you'll notice about this question is that the bases 2 and this base 2 are equal to each other. And so really we have a situation where we're saying that the things in the exponents, so x minus 1, has to be equal to 2x minus 4. Right? And kind of as a side note for you, if I had 2 to the x equals 2 to the 5th, I think you'd all be able to tell me that x equals 5. And that's exactly the concept that we're going to apply to this question. Alright, so because the bases are the same, I can just take the exponents, x minus 1 on one side, and set it equal to 2x minus 4. And I'm going to go ahead and subtract the x to this side, and I'm going to add the 4 to this side. So negative 1 plus 4 gives me 3. and 2x minus 1x gives me x. And so I've got my x value, and we're going to go ahead and make sure that we check our answers here. So when we do that, we get 2 to the 3 minus 1 equals 2 to the 6 minus 4, or 2 squared equals 2 squared, and we're good to go. All right, so let's take a look at example 2. Now, unlike example 1, I notice that I have bases. One is the 3, but the other base is a little different. It's not a 3, it's a 9. And so I can't just write 5x minus 8 equals x plus 2. Okay, let me write that in red because I can't do that. So 5x minus 8 is not equal to x plus 2, and that's because the bases are not the same. What we can do, though, is make this base look like the other base. And we can do that just by thinking about another way to write 9. And another way to write 9 is 3 squared. So I can replace that thing in the orange, the 9, with the 3 squared. And I'll still have the x plus 2 in the power. All right, now let me clean that up a little bit. We've got 3 to the 5x minus 8 equals 3 to the 2x plus 4. Now we've made it so that the bases are the same. We've got a 3 on this side, we've got a 3 on this side, which means that we can go ahead and set the exponents equal to each other. So 5x minus 8 is going to equal 2x plus 4. So 5x minus 8 is going to equal 2x plus 4. I'm going to subtract the 2x to this side, and I'm going to add the 8 to this side, and I'll get 3x equals 12, or x equals 4. Okay? And if you go ahead and put that 4 back into your original question, you'll find that it does work out. And so x equals 4 is our solution. All right, we're going to take a look at one more example here. And we'll notice that very similar to example 2, I have a base here of 1/3. On the other side, I don't actually even see a base. So we need to move some things around first, okay? I'm going to take this 36 and I'm going to divide it to the other side. And let's see what we get when we do that. So 1/3 to the x over 5, don't be scared of all the fractions, it will be fine, equals 4 divided by 36. And 4 divided by 36 we can actually reduce to be 1/9. Now the reason why I want to reduce that is because that's actually going to make my life a little bit easier in terms of trying to get things into the same base. So my left side is still 1/3 x over 5 equals, but instead of writing 1/9, I'm going to write it as 1/3 squared. Now this is really nice because what I've done here is set up a situation just like example 1 where the bases are the same, and now I can take this exponent and set it equal to this exponent. All right, so we've got x over 5 equals 2. And to get rid of that 5, I'm going to multiply it, so x equals 10. And you always want to check your answers. When I plug that back in to the original equation, it works out, so x equals 10 is a solution. All right, we're going to leave our solving equations for a little bit. We'll come back to them at the end of the chapter in 4.6. For right now, we're going to go back to the graphs that we saw earlier and talk about graphs and graph transformations of exponential functions. So, some important features of an exponential graph. So again, we want to make sure that we know this equation, f of x equals a to the x. Anytime we see the variable in the exponent, we're thinking exponential function. Now, this exponential function has a few important features. And the first one is that there's a restricted range. And all that means with the restricted range is that you only have positive y values in this parent function or in just the a to the x graph, okay? And if you look over at the picture here, you only see values that are above the x-axis. The second important feature about this is there is actually a horizontal asymptote. That doesn't necessarily show up when you graph it on Desmos or on your graphing calculator, but right here, there is a horizontal asymptote, meaning the function gets super close to this line, this imaginary line that's not part of the function, but it doesn't actually touch it. And the equation of that line is y equals 0. And the last important feature that we've got going on here, we've got a y-intercept of 0, 1, and that corresponds to that point right there on the graph. Okay, so we're going to take a look at some ways that we can move this function around, but see what it looks like based on just the equation, okay? All right, so here are two main transformations that happen. One is a horizontal shift and one is a vertical shift. So a vertical shift is going to correspond to having a to the x plus some number at the end. Now, if it's a plus d, you're going to be moving your function up, whereas if it's a minus d, you're going to be moving the function down. And as you move the function up and down, that is actually going to change the horizontal asymptote. And so just to kind of give you an idea of what that looks like, I could take a regular exponential function, and if I said y equals 2 to the x minus 3, that's going to correspond to this case. I'm going to move the function down 3. In fact, my horizontal asymptote is now y equals negative 3. And then I'm going to have the rest of the graph following that very same shape. Let's move on to horizontal shifts. So when we have a horizontal shift, the location of the number in our equation changes. It's actually going to be up in the exponent with our variable. And anything that's horizontal is always going to be the opposite of what you think. So in this case, a plus c actually means move it to the left, and a minus c means move it to the right. And this one does not change that horizontal asymptote. And we'll do a quick illustration so we can see that it's not changing. So if I take a regular exponential equation, y equals 2 to the x minus 3, okay, so same numbers as the other example, but I changed the location of the 3 in the equation. This minus 3 means I'm moving my graph to the right. And so that y-intercept gets moved over, but my horizontal asymptote stays in the same place, whereas in the vertical shift, this one got moved down 3 units. All right, another common set of transformations is when we have reflections over different axes. If I have a negative sign in front of the entire equation, that is going to be a reflection over the x-axis. This is not going to change the horizontal asymptote. And in an equation, you might have something like this. Y equals negative 2 to the x And instead of being above the x-axis, now it's going to be flipped down below. And that horizontal asymptote stays in that same place. You could also have a negative sign up in the exponent with the x, and that's going to cause a reflection over the y-axis. And just like the other reflection, it does not change the horizontal asymptote. And let's take a look at a picture. I could have y equals 2 to the negative x, and that's going to flip it so that it looks something like this. And that horizontal asymptote, just like in the other reflection, stays where it is. Okay, let's take a look at two different examples here and see if we can just describe the transformations that are happening. So I notice that I've got a few numbers here. I've got this minus 100 up in the exponent, and I've got this plus 200 that is not in the exponent. So that minus 100 is going to go ahead and move the function to the right 100. And this plus 200 is actually going to move our function up 200. Now, this one will make our horizontal asymptote move to y equals 200. If we take a look at example 2, we've got a few different transformations here. So we've got a negative in front, so I know there's a reflection, and I've got this minus 5 at the end. So this negative in the front is going to go ahead and reflect over the x-axis, and this negative 5 at the end is going to move the function down 5, and that will move the horizontal asymptote to be at y equals negative 5. All right, let's take a look at one last example here that I think is a little bit trickier than the other two because we have to do some manipulation before we can actually see what kinds of transformations are happening. So I'm going to go ahead and rewrite this function. So I have e to the negative x plus 2. Okay, that's the first thing I want to do. I want the x to be in the front. The next thing I want to do is I actually want to factor out that negative. So negative times x will give me negative x, and then a negative times a negative 2 will get me back to that plus 2. So I want to be really careful about that sign change here. All right, I want to make sure I don't miss that. But once I have that, I can identify the transformations that are happening. So I've got a minus sign in the front here. That's going to be some sort of reflection. And I've got this minus 2 in the exponent, which is going to be a horizontal transformation. So the graph transformations that are happening here, I've got a reflection over the y-axis, and I'm moving it to the right 2 units. All of this means that horizontal asymptote is going to stay at y equals 0. Now you're welcome to pull up Desmos for any of these graph transformations. All right, let me write that down. Desmos has a really great free online grapher tool, so it could be of great help to you when you're trying to figure out what transformations are happening here. Okay, we're going to finish off with some applications of exponential functions. These are probably some of my favorite applications of all of the different functions we learn in pre-calc because it's so real. We use this a lot when we talk about populations. We use this a lot when we talk about money. And I think those are things that are relatable to a lot of us. Before we get there, let's take a look at the general equation for an exponential function. And let's talk about what the different pieces mean. So, this y over here, that y stands for the ending value, okay? Stands for the ending value. This b that is in front of our a, that b actually stands for our starting value. Sometimes we call it the initial value. Okay, this A is a letter we've seen before. And this A is so important, I'm going to write it off to the side. This A is our growth or decay constant. Okay, this is our growth or decay constant. In a lot of our word problems, we're going to see percentages. Okay, the percent that they give you is not your A. So let me write that out. The percent that they give you in the word problem is not your A value. Don't be tempted to just plug that number in. What you do have to do is a little bit of work, and I have this handy formula so that you can remember how to find your A, because you're going to need it to write your equation. And you can find it from the percent. So to find A, you're going to take 100, the number 100, you're going to add or you're going to subtract. Okay, so it's not both. It's not like in the quadratic formula where it's both, but you're going to pick one. You're either going to add or you're going to subtract whatever percentage they give you in the word problem. Then you're going to divide by 100. Now, the way this works is the 100 stands for the amount that you started with. You started off with 100% of things. The plus sign, you're going to use the plus sign. I already used orange here. So the plus sign is for the case where you have growth. Ooh, so many colors. The minus sign, okay, this minus sign down here, that's what you're going to do if it's a decay situation. That percent at the end will help you determine what's left, and then the 100 on the bottom turns it into a decimal for you. So you don't need to turn anything into a decimal. This dividing by 100 will turn it into a decimal. Last but not least, in our problem, we've got our x value up here, and that x value, I'll draw that down here, that x value stands for time cycle. All right, so it stands for time. The cycle part is actually going to be important when we get to our third example here. Okay, so to summarize before we move on, we've got y equals our ending value, b equals our starting value, a is our growth or decay constant, and x is our time cycle. Let's get started with our next question. Okay, so Erin decides to purchase a brand new Toyota Tacoma for $36,000. If her truck depreciates by 17% each year, Write a function that models the value of the car. Then find the value of Aaron's truck after 7 years. So there's one word in here that I want us to be aware of, and that is depreciate. Okay? Now, depreciate just means that it's going to lose value. And that is a reality with most of the cars that we buy. As soon as we drive it off the lot and every single day that we use our car, it goes down in value. Depreciation is not a word we ever want to describe, say, a house that we own, because we don't want that house to go down in value. We want that house to appreciate or go up in value. Okay? But in this case, we're looking at depreciation. And we want to make sure that we identify that percentage, because the percentage is going to help us find our A value. Remember, 17 is not your A. We can, however, also identify our initial value or our B value from our equation. That's usually pretty straightforward in the word problem, okay? And so what we're going to do now is we're going to go ahead and write our equation. So y equals our starting value times 100. Now, I should do not the plus, but I should do a minus because my car is losing value. So 100 minus 17 over 100. And I'm going to raise that to the power of x. If you want to clean that up a little bit, I would suggest turning that big fraction inside of the parentheses into a decimal. So 100 minus 17 will give me 83. 83 divided by 100 will give me 0.83 to the x. Okay? And on an exam, you can just write this part for me when I ask for the function that models it. That totally works. And then the second part of the question says, find the value of Aaron's truck after 7 years. Now, since 7 years is a time, that means that 7 is our time cycle. So to find her value of the car after 7 years, we're going to do 36,000 times 0.83 to the 7th power. Now, for some reason, students always forget the order of operations here. And so I just want to make this super, super clear for us. When we type this into our calculator, we need to make sure we do this part first, okay? Exponents come before multiplication. And so I'm even going to take the time to write that out, whatever decimal I got, which turns into 0.27136 with a lot of other decimals after. And then I'm going to multiply my 2. Now the units that I'm going to put on this is the value of her car, so I'm going to put a dollar symbol. And then you'll notice that your answer has a whole lot of decimals. And a good question that students always ask is, how many decimal places should I round to? And since we're talking about money, I'm going to say, let's go to 2. 2 for the cents, 98 cents. Okay? So Aaron's car in 7 years is worth less than $10,000. And that's just from normal driving. Okay? So this is a pretty good example of why some people might say, I can afford a new car, but I'm going to buy a used car because it might save me some money. I'm not suggesting that you buy new or used. I'm just saying it's something to think about as you are purchasing a car. Okay. Example 2. Manatees, very adorable creatures, have recently been removed from the endangered species list. True story. If there are currently 13,000 manatees worldwide and the population is growing by 1.5% each year, determine how many manatees there will be in 5 years. So I see the percent, and I'm saying, I got you. This is an exponential equation. And then I'm going to fill in the values I need. So the initial number of manatees, or the starting number of manatees, 13,000. I don't want to put 1.5 in here. Don't do that. But you can do 100 plus, because the number of manatees is growing, 1.5. And then you want to make sure to turn that percent into a decimal by dividing by 100 and putting it to the power of, in this case, 5. I'm going to go ahead and turn the thing inside the parentheses into a decimal. And just like in the other question, I better do this part first so that I don't mess up my order of operation. And I'm going to get 13,000 times 1.077284, lots of other decimals. And I'm talking about an animal right here, so it might be best if we just round to the nearest whole number, because we're not really considering pregnant manatees, we're just considering ones that are actually born. And when you do that, I believe you get 14,004 manatees. Okay, so we've talked about buying a car. We've talked about populations getting taken off the endangered species list. And we're going to finish off this lesson with another classic case, which is half-lives. Now, one of the things that I don't love about half-life questions is they give a lot of distractor numbers. And so there's one number that I'm going to ask us to go ahead and cross out right now because we don't need it for this question. And that is this number, the 197. We're not going to use that at all. That's just a descriptor to talk about the thing that is used in kidney scans, okay? We will, however, use the rest of the numbers. So let's see. I see the word half-life, and I'm thinking y equals b times a to the x. I start off with 12 milligrams of this sample, so 12 is my B. To find my A, a half-life means that you're losing 50% of your material in the given time. Since I'm losing 50%, I'm going to do a minus 50, and then I got to turn that into a decimal by dividing by 100. Okay. Here comes the tricky part for this question, though. You'll notice that there are two other numbers that I haven't used yet, the 64.128 and the 72 hours. Now, the 64.128 means that in 64.128 hours, my sample will have half as much as I had at the beginning. And then in another 64.128 hours, I'm going to have half of my half. And then in another 64.128, I'm going to have half of that half. And so the thing I don't want to do here is I don't want to go ahead and just put the 72 up here. All right, we're used to putting the time up there, but that tells me how many hours when really I want to find out how many half-lives. So in order to do that, I'm going to divide by how long my half-life is, okay? So this is how many half-lives. My suggestion would be to turn a lot of things into simpler numbers. So 100 minus 50 divided by 100 will give me 0.5. And by the way, for every half-life, it's going to be 0.5 in there. And then I'm going to turn that exponent into a decimal. And when I do that, I get 1.122754491. Now you might be asking why I'm including so many decimals, and that's because the sooner I round in an exponential function, the less accurate my answer is going to be. So I usually try and take as many decimals as I can until I get to the very end, okay? Now, just like before, we're going to go ahead and make sure we do this part first before we multiply in the 12. And so we'll get 12 times 0.459216 and a bunch of other decimals. And when we multiply those two, we'll get 5.51 milligrams. Okay, so that ends our lesson here for today. If you have any questions, shoot me a message on Canvas, send me an email, and I'd be happy to try and answer that for you. All right.